everyone, how are we doing? Start the project early. That's the theme of that intro right there. What questions are there? Who all is here? Let's see. Start pulling up some assignments. Do I have the project open? I do not know who all is here right now. Say hey if you're in the chat. Mubot is awake, I think. Let me re-wake up Mubot right here. Mubot. Wake up Mubot. There we go. There. Hey, what's up, Paige? Good to see you. Which one do you want to do on quiz 14, Paige? Feel free to ask. Good to see you here, Leslie. Whichever question you want to do. Let me go get those. My Pearson. Up, there we go. Log into my Pearson. Mubot is awake. Let's see. I can see the chat now on the other screen. Maybe. Hey. Let's see. I am pulling up quiz 14 as we speak. The flight one? Sure, yeah. We did one of the flight ones yesterday. Let's do the other flight one. Quiz 14. And we almost have it. Here we go. And there we go. And I think it's around here. Let me get ready for the flight one. Here we go. Found it. Let's do it. Here we go. Okay, here we are with the flight question. This is the flight question right here. And let's start out. What are our three conditions? We have three conditions, which are random. We need to randomly select these flights. So are these randomly selected flights, which would mean they're independent sometimes, and some of these point this out, that if they are random, they'll be independent. See, it doesn't really say, but I hate that. I hate the questions that don't really say. So you have to assume, hey, good to see you here, Kayla. Can you do the nutrition lab one next? You got it, Bailey, of course. Is the randomization, so they're splitting it apart, which is okay. Are these less than 10% of all flights? You bet they are. Is the nearly normal condition met? So a few people were asking about this last night, and I kind of changed around the quiz to hopefully help out. I removed the one question that I really think wasn't clear. The nearly normal is the condition, and the way it can be checked is large enough n. So we can check the nearly normal by way of the large enough n. Sometimes we see if n is large enough. Do we have a BS? We will, yep. I'll be releasing a layer tonight. I got a little bit behind getting all the work done. So we will have an assignment this week. Expect it released later tonight. Monday for extra credit. Tuesday for regular credit next week. So sorry, Kayla. So sorry, Kayla. It's going to be on Logistic. I could talk Logistic here after the next question if you want, Kayla. So we could talk over some Logistic. And it'll go through Logistic a little bit with indicators with Logistic, a little bit of that. So, yay. Sorry for the delay. End of semester. Oh my gosh. Semester is just so, it flies. It flies. Seems like just yesterday we were starting, and now it's like we're just 2 weeks away from done. I just can't believe it. Is the nearly normal condition met? This distribution right here is pretty normal. Can we go over how to make it? Yeah, this is, and that's what we're doing right here. We'll make some confidence rolls right here. So this meets all the conditions right here, Parker. This is nearly normal, and the large enough n condition, or excuse me, the nearly normal condition met by the large enough n is what we have going right here. Yeah, definitely, Kill. You got it. And so we meet all the conditions right here. Now we get to making a confidence interval. So to make the confidence interval, we need to use the proper formulas. So to make a confidence interval, we need the proper formulas. So I think, there we go. That does have all the information. So it's if you know, there we go. If you know the right formulas, it helps out a lot. The right formula for this, I know, right? Page, it's the page, yeah, it's just, it blows my mind. Y bar plus or minus t with n minus 1 degrees of freedom, s over square root of n. So what are we missing right now? We're missing two things kind of with this output up here. Who can explain what we're missing? This is the hard part where usually people get stuck on this problem, and I've put something in the chat to help us out. What are we missing? You can see pretty much everything here except for a certain thing. And then we know we have to go here and we have to know this to use it. So what are we missing? Oh, Mubot's talking to us. What are we missing? To make a T interval, which Mr. T is mean if you're doing drugs. Make a count, and why do I say that? Mr. T is mean because T means, so quantitative. So since we're doing the mean right here, I always say Mr. T is mean. You're doing drugs. And so that's how we remember that when we do the T interval, we're doing means. We're doing quantitative data. So even if we don't know the equation, if we know we're making a confidence interval for the mean, we would know we're using the T interval, just or T mean. So that's a good way to just keep it in your head. We try to just store a little bit up here, and after a while it becomes just commonplace to be like, oh, it's a t-interval. It's used to estimate the mean. 2t interval used to estimate the difference between two means. So 2t, two means. So we'll talk about this more right here, but what are we missing here? What are we missing? And we also need to know one more thing. I forgot to check what it wants. 90% confidence. That's going to be very important when we go to 90% confidence. So 90% confidence, it wants a t-interval of 90% confidence, and it also wants 71 degrees of freedom. Note how in the formula, we do n minus 1 right here. This is the degrees of freedom. So we know using this that we want 90% confidence. Let's go right here. We're going to go to a confidence interval, which looks like this. 90% confidence, 71 degrees of freedom, and here's the t statistic of 1.667. So that'll be the t. So degrees of freedom is equal to 71. The t for this is equal to 1.667. And now we go down here, y bar is 80.2639 plus or minus 1.667. And then s over square root of n, 2 points. They really like a lot of decimals here. Carry your decimals. So I always solve for the, I'm probably blocking some of this. I'm not, look at that, I'm not blocking it. So I always solve for the margin of error first. So let's solve for the margin of error. And to solve for the margin of error, we go here and we go square root of 72. That's the bottom right there. We're going to copy this, and then we're going to type 2.75862 divided by that. And then we're going to times it by 1.667. And that is the margin of error. So everything I've just solved for right here is this. Like if I make it a little bit wider, I think I'll change the calculator. There we go. So it's 80.2639 plus or minus this. So kind of just reading the formula across. So we now have the answer to what that is. And let's go ahead, and I did do 90%, right? Yesterday my brain was off. I was getting wrong answers. We don't like that. So let's go right here and do the mean. 80.2639 plus this. 80.81. Is it 2 or 1? Now be careful because I have definitely entered in the wrong amount of decimals. And that's how I got one wrong yesterday. And we still have the margin of error in here. There we go, 79.72. There we go. Interpret the confidence interval. I am 90% confident the true, it's like, it is a percent, isn't it? Or the true percentage of flight. So they are doing percent, but it's like on average the percent. So they're not doing a proportion. They're doing like an average percentage, which they're going to use a quantitative amount for that. A little bit interesting of a question, at least theoretically, what they're doing. So let's go right here. One can be 90% confident the interval contains the true mean monthly percentage. That sounds about right. There's nope. So just think, I am 90% confident the true mean monthly percentage of online departures is contained in the interval blank to blank. That's how we do our interval right there, just to make sure people remember. I always read off my interpretation this way. Why is everything appearing over there? Whee! So I always say, I am blank percent confident that the true blank is contained in the interval blank to blank. So this is just your practice way of reading right here. Always interpret it on your own first. That's how to just make sure you get the right answer. I am 90% confident that the true mean monthly percentage of online departure times for flights is contained in the interval blank to blank. So when you look at their answers, I am 90% confident that the true mean monthly percentage of online departure times is contained in the interval blank to blank. It has all the components I use for my default one, just moved around a little bit, and they say we are, we can. That's totally fine. Yep, there we go. That's how we do it. Let's see here. The other one was Nutrition Lab. Are they doing the yogurt stuff? Yogurt. Nutrition Lab. That's not the Nutrition Lab one. Psychology experiments. Golfers. We haven't done the golf ball one lately. Where's the Nutrition Lab one? A Nutrition Lab. Here we go. Okay, let's do the Nutrition Lab question. I put these cuts in the video so we can back and find it. And then I think Caleb will do some work on some 320, talk about those concepts. Let's check out this right here. Okay, so we have some summary statistics. We have 323 and 37. I need some help though, and we have 60 right here. Can anyone identify any of the notation in this question? I need some help from anybody. Who can help identify some notation in this question? Who's watching right now who can be like, Brian, this is this in notation. So knowing the notation is key to solving any of these questions. If you know the notation, it makes life a lot easier. I'm going to write the formula right here for the confidence interval for the mean, because it wants us to build a confidence interval for the mean. It says find a 95% confidence interval for the mean. So we should go to our formula sheet and look at y bar plus or a minus t with n minus 1 degrees of freedom. That's a subscript. It's like saying like it's a specific kind of t. It's not saying times it by n minus 1. It's just saying this t has this feature to it. It's like this is this thing with this feature. It'll go away once we find it. We won't put the subscript next to it anymore, but those are the degrees of freedom. And next we have s over square root of n. So now we have some numbers up here, and you'll notice we're short on some stuff. We don't have enough because there's 1, 2, 3, 4, 5 things. And so what do we have up there? And we're going to need to go find one of them because we can find four of these things pretty quickly right here. So we have to know what each one of these things are. Nice job, Kayla. Kayla, just awesome work. Kayla, great review, everything. Yep, this is going to be n right here. This is going to be y bar. This is going to be s, and there we go. Sample standard deviation, sample mean. And make sure always to say sample before these, because this is not the true mean. This is not the true standard deviation. It's the sample standard deviation from a sample of 60. The 60 hot dogs had a sample mean and sample standard deviation of the following numbers. Now the tricky part right here, and we'll put it in the chat again, which it's right there, but why not MuBot? So the t distribution is really going to help us out right here. We have to go and find the degrees of freedom. The degrees of freedom for this are going to be 59 because n minus 1. So I put that right there next to that. It's n minus 1. And we go to the t-applet now. And the whole thing about this t right here, this t with n minus 1 degrees of freedom, means it's going to tell you which t distribution it is. And I wonder, Kayla, have you done a lot with distributions? And you've probably integrated these curves, right? Like in mathematical theory or mathematics, you will take these curves and actually integrate them. But what we do a lot of times is we just enter in the degrees of freedom. We enter in the percent confidence we want. And please note, I've put this down here to this. This is a confidence interval because it contains the middle 95%. Confidence intervals contain the middle area of a curve, unless there's ways to do one-way confidence intervals, but we don't do those in our class. A common confidence interval, which is this one right here, will go from plus or minus a certain amount and have a margin of error. The t-score is basically 2. And the t is basically the z, especially if you give it a lot of degrees of freedom. It will become the z with infinite degrees of freedom, technically. But the lower the degrees of freedom, the less it is like the z. So at this point, we really need to use the t because there's, the z-score is 1.96 or 1.95996. It's scary, Kayla. I always like memorizing numbers. And so I put more and more numbers in my head. It's a bad habit, putting all those numbers. I've always liked memorizing it. It always kind of, I put that in the wrong spot. Speaking of, I don't know how to write formulas. I find memorization interesting, that our brains can hold a bunch of information as though there's information just floating around in our brains. I haven't integrated T6, we were doing the most integrated parts, probability of continuous random variables. Oh, yeah, that makes sense. Yeah, no, you're doing some really cool statistical stuff. Like, if you ever consider like doing a PhD in these areas or anything like that, that's the kind of knowledge you would want to have in Math 323 right now. Yeah, that's the kind of stuff I was missing when I was doing a PhD. I did a PhD for a little bit and then said, you know what? This is a lot of work. Not that I want to be like, oh, it's too much work, but yeah, it was pretty intense. We're just timesing out right here, finding the margin of error. Master's degree is difficult. PhD is like your life. I mean, that's what it should be probably. But I didn't have the time. I was teaching, so I couldn't dedicate my life to the PhD. I have students. So there is the margin of error. The margin of error is just the plus or minus on the interval, 323 plus or minus this amount. Is this one we got wrong yesterday? We got like a little bit wrong. So we just go right here, copy this, 323 plus this, 1 decimal, 332.6. And then we go here and we take 323 minus it and 313.4. What assumptions have you made to do this? We assume that the hot dog weights are independent and they are normal. That's pretty much your nearly normal condition right there. Is the randomization condition satisfied? It doesn't say that they're random, but sure, why not? Is the 10% condition satisfied? So we need to sample less than 10% of all hot dogs. So yes, hot dogs, the 60 hot dogs count for less than 10% of all hot dogs. Is the nearly normal condition satisfied? We don't know, but since there's 60 hot dogs, 40 or more is probably good, because as long as they're not heavily skewed. I wish they showed the distribution. Explain clearly what your interval means. I am 95% confident that the true mean sodium content of these reduced fat hot dogs is contained in the interval. Boom. They just don't give you the interval there because they don't want you to see the answers. And there we go. There we go. We got it. Let's head over to, let me head back to space right here. I think you have enough experience now that more education would not increase your... Yeah, exactly. Oh, wait, per last week's interview. Oh, wait, is this... Oh, haha. Kayla, you might be right. Well, two things. One, it's like a personal goal of mine to get a PhD. I've always had the utmost respect for people who reach the terminal degree. I've always kind of wanted to get myself to that level of education. And I wouldn't have people call me Dr. Stevens. No, but I'd like to know in the background of my head, like, I achieved it. I got to Dr. Stevens. My brother's a doctor. He's a doctor of pharmacy. I'm feeling confused. I keep doing the flight problem. How did you get an interval? How did I did get an interval wrong? Mine does say the conference roll arrived late, but yours on time. Oh, maybe it's the other one. Here, we can do that one real quick here. We'll do that one, and then we'll hop over to Kayla's stuff. So that way, because I'll go to Kayla's stuff for a little bit here. Paige, do you want to put your numbers in the chat? If you can put your numbers in the chat, I'll solve your numbers. And let me see. There's 2 flight problems. There are 2 flight problems. Here's the on-time one. Tell me if this is the one. Is this the one right here you're doing, Paige, or is it the other one I was doing? So does yours look like this, or does it look like the other one? We did this one yesterday, but feel free. Let me see if there's another flight one. My goal is to get PhD in math and won't make people call me Dr. But I would encourage it. Yeah, exactly. No, that's awesome, Kayla. Yeah, you'll probably have a lot of recommendations, but obviously you have my recommendation. But even if you don't need it, keep up the great work. And then what % confidence here? We'll solve Paige's problem right here. So Paige, we're going to double check your work right here. And thank you, Paige, for hanging out. Let's double check the work. You ready? What % confidence does it want, Paige? So the formula is... $99. What T-score did you get, Paige? I'll double check. It might be your T-score. No, that's all right, Paige. That's all right. What T-score did you get? So I think that's going to be the issue. Let's see which T-score you got. I think that's going to be the issue. That looks about right. 2.647. Let's find it the really good way. You ready? PT. It's QT. I always get QT and PT mixed up, Kayla. It's 71 degrees of freedom, right? 2.647. Yeah, this is the more exact, so you are correct on that. It's going to show on the applet 2.647. So here, we won't worry about my version. We'll go to the applet, and I'll show you, because this is what... And it looks like you did everything correctly. this is what you're seeing right here. I doubt it's going to be the decimal places that this is just more accurate. You can do amazing things with this, which I love, is you can go here to like options, digits equals 20, and SciPen equals 20. And now we rerun this. And if you really want to go crazy exact, you know what let's do? Let's solve it in here, and I'll explain why. Because we can solve this out exactly. So I'm going to solve out like exactly your interval, like down to the decimal, because let's go right here and show that we're just going to take this number and plug it in right here and do 2.647. So this is everything right here. Does that make sense? This is what you should have mathematically. And checking it out right here, let's take your mean. Let's get the margin of error first. Okay, margin of error, or let's do standard error. Standard error is equal to the standard deviation over the square root of n. So there's the standard error. Margin of error is equal to the t-score we were just getting. Where'd I go? Here's the t-score times the standard error. There's the margin of error. And then we take the interval. So this is the upper is equal to this plus margin of error. And then the lower is equal to this. And then we say something like cat paste. I am 99% confident that the true mean flight time is contained in the interval. And then go here and go lower. Is it mad about those spaces? Cool. 2. This should show right here what the answer is. Ooh, it's mad about something. Oh, there. Oh, it does the spaces right there. I don't like that. let me change the SciPen all around. SciPen 7. Oh my gosh, what happened to my... Did I run SciPen in digits? Well, sure. Is this what you're getting right here? Can you explain the flight question on chapter 14 homework next? Sure. I think I know which one it is, Bailey. Are these the answers you're getting right? Oh, I did my lower and my upper reverse. Oh, because margin error is negative. So let me change this. Well, you know what we'll do? We'll go to margin of error and we'll go ABS if Kale's watching. And we'll go absolute value of the margin of error. And there we go. Now it's looking like that. Are these the answers you're getting here, Paige? These should be the right answers. 71.24. So it should be just round to the right decimals. I think, oh wait, Y bar. Oh my gosh. No, this is, Brian can't read is what the answer is. I put the sample size right there. Okay. 24.45 and 24.96. It's saying it's wrong. Those are the exact answers I'm getting right there. Make sure, does it say to round to 1 decimal or 2? Sorry about that. I made a mistake. I grabbed the wrong thing. I grabbed the sample size. It looks like you're doing it correctly. And it says you're wrong. I might check out the answer here and then we can do Bailey's question. But this follows through all the mathematics down to the every decimal we could carry. So this is pretty crazy right here. And we could fix this so that if it rounds to 2 decimals, we could just take this right here and do the following. And this is why I like using programs like this, because, you know, like we just let it do all the hard work for us and we don't have to worry about whatever we put into it. And so there it is right there. And that's it. You're getting exactly what I'm getting. So let me double check. Do you want me to double check this real quick, Paige? Because you're getting exactly what I'm getting right here. And also we can use this to solve for any problem now. Like we could check anybody's work on this now with this. Like we could just change. Truthfully, what we could do is if we need sample size. Yeah, we can change. I'll do it later. I don't need to program something right now. Basically, Cal is going to program it so we could just enter in the values of what the sample size is, what the standard deviation is, what the confidence level is, and we could just put those in. It doesn't like those, Paige. Paige, I'll go look at the thing, and then we'll do Bailey's here next. Let me go look at Paige's problem. Let me see. Is this the right? I've got a page. Yep. Okay. What does it not lie? Okay, I found it. Oh, wait. I think, Paige, you might have reversed some numbers on it. Wait. It says your numbers look correct, but it's showing you have different numbers entered in. It's showing 23.64 and 24.78. Let's see if Paige responded. Those should be the right numbers. And if you want, Paige, I can show your problem, and I can look at all the numbers here. Let me see if we have all the exact same numbers. Yeah, that's that. Yep. I'll wait to show, but I wonder if I can answer in the numbers. Let's see what it does. 23.45. And can I check them? It won't let me check them, but it shows the different numbers entered in. Paige, let me know if you have any issues with that. I don't know why either, Paige. Don't worry, it happens to me sometimes. Yesterday I was having my brain was not working yesterday, and I don't know. I was like, what? And Bailey was wondering about. Great job, Paige. These are harder quizzes and everything. These are harder quizzes, so I understand. Like, they're basically, it's like if you make a single math error, everything just goes crazy on these quizzes. You make one little decimal error, you forget to enter in one decimal, everything goes crazy. We're 100% today, though, which is good. We should be able to get hundreds. I think Bailey was wondering about the other question. Bailey said, and then we'll do Kale's question next here. Bailey said, can you do the flight question on Chapter 14 homework next? I guess, yeah, let's go look at the Chapter 14 homework. What am I doing right now? Cool. All right, Chapter 14 homework. Flight question on the homework. Let's go take a look at it. There are 3 questions. Okay. We did that one yesterday. Nutrition laboratory. Here we go with the flight. Got it. Okay. And here's the flight question. Let's do this. Okay, with this one, we're given summary statistics, and we're asked to check some conditions, but don't be tricked. Don't be tricked by the conditions. Looking at the conditions first, we see that all of the assumptions are met, which means we have randomly collected data. Sure. Less than 10% of all flights, 72 flights would be less than 10% of all flights. That totally makes sense. And condition 3, we need to meet the nearly normal condition, which is often met by way of large enough n, saying that the sample size here of 72 is large enough such that the distribution of the mean will be nearly normal. So I think we did well. I think we've got it. I think all conditions are met. Going on, yeah, met all conditions. So now we have to make a 99% confidence interval, and this is where people usually get stuck, but the formula will help us out. We need to look at the formula right here and think about what we have and what we need. So let's go ahead and grab the notation right here. Boop. And hop right here to a new data sheet. And Mubot's already put in the chat the t-interval calculator. And we need to write down the formula. So it gives us most of the parts right here. It gives us most everything we need. And we have here y bar. This is the formula we can look up. T with n-1 degrees of freedom, that is subscript right there, s over square root of n. So what we have here is the sample mean given to us, plus or minus a t-statistic, which is going to have a star. We sometimes put the star here to denote we pick it based on the level of confidence. It did say 99% confidence. That's going to be important for the t-statistic. So that whole star thing means it's relative to a certain percent confidence right there. The n-1 degrees of freedom, let's go ahead and solve for that. This is called the degrees of freedom down there. So df equals to 71. And all we're doing is just taking and solving n-1 right there for the degrees of freedom. So we know what the degrees of freedom are. We'll go and get this t, why not right now? Let's go do it. So when you put this in the chat, you can look in the chat right there. This is the t-applet from statdistributions.com, one of my favorite ones to use. And when you make intervals, you will go down here to the following because it plots the middle percent of the curve. For some reason, it's showing 50%, but we want 99%. There's 99%, and we want 71 degrees of freedom. Why 71? Because we're doing n minus 1 degrees of freedom. As noted right here, star means the confidence relative to 99% because the problem said so. And there's the t statistic right here for plotting the middle 99% of the curve on a t with 71 degrees of freedom. The degrees of freedom control how normal the curve is. The more degrees of freedom it has, the more normal it'll become, and your t-scores will start to look like z-scores, as is the classic 1.96, which when you have a lot of degrees of freedom, it'll look like this. But if you don't have a lot of degrees of freedom, it won't look like it. More degrees of freedom, closer to the normal. But do remember, we're working with 71 degrees of freedom and 99% confidence, plotting the middle 99% of the curve. Make sure you're plotting the middle of the curve. You can see here, there's some on the outside not shaded and some on the inside shaded. The middle 99% is shaded, and here's the t-score right there. Let's go ahead and take that t-score, 2.647, and I'll just go right here. Oh my gosh. And we need the y bar. Oh man. I'm not good at writing small. And then S. When I was a kid, I used computers all the time. That was in the 80s. You're like, what? Computers? No one's going to have a computer. Computers? You have a home computer? What? I'm very lucky to have a home computer. Like, you had a home computer? Psh, everyone's got a home computer. Not back then. Not in the 80s. 2.52190 divided by this times 2.647. We have just now found the margin of error. So here is the margin of error. I just like to put it right here so we can see 24.3889 plus or minus the margin of error. Let's go back to the question right here. And we're just going to take and do the sample mean plus or minus the margin of error. So make sure you have the margin of error copied. 24.3889 plus the margin of error, and that'll be 25.18. And then we go back and we do 24.3889 minus the margin of error, and that'll be 23.60. And that should do it. Nice. Interpret this interval. I am blank % confident that the true blank is contained in the interval blank to blank. We've got that written out today right here. Where is it? There we go. I am blank % confident that the true blank is contained in the interval blank to blank. So what does this mean? I am 99% confident the true proportion of on-flight times for the monthly measures are contained in the interval blank to blank. So we're talking about we can be 99% confident the interval contains the true mean monthly percentage of delayed flights. We're talking about delayed flights, actually. And that's got it. I think that does the question right there. Excellent work. That is the question right there. Good job. So let's take a look. We'll hop back to space. We'll take a look.
It's not the question you deserve. It's the one you need.
I need to use that more often. I just never hit the buttons. Let's go take a look. Kayla, if you're still around, we'll take a look at some logistic regression. Let's take a look at that. So logistic regression. Logistic regression. A little bit of logistic regression right here. Could you please go over the multiple choice on what is true? Yeah, let's do that. We got that next year. We'll do it in about 5-10 minutes. Grace, you got it. We'll talk over a little logistic here, and then we will do that next. Awesome, Kayla. So in logistic, you have to know this. This is the most important thing for logistic. And it gets confusing. It's like, wait a minute, how are we doing a categorical Y? What trick did we do previously with indicators to use if a categorical was happening or not happening? We described them as what or what, which we'll see right here. I'll make a logistic model as we talk. And then we talk about the trick we did, which we're doing the same sort of trick right here with logistic to predict a categorical Y. We're going to do the same sort of like on-off trick to make predictions on it. and we can talk about what we're actually predicting then. Let's go right here. I did this yesterday at the end of class, and I made a mistake. I was like, no. Yep, exactly. We're going to use 0, 1. And what we're actually predicting now is the probability. And we have to change up what we're doing. As long as I spelled everything correctly. There we go. Cool. So here's what it looks like. And I want you to just think about this. So how would you describe the probability of being male related to height? So just look at the curve and just take it in for a moment. This is what logistic regression is. And it's a sigmoidal curve. We call it the sigmoidal curve because it's S-shaped. So this is the sigmoidal curve, S-shaped curve. And this is logistic regression, which, funny enough, is actually on our Know Your Graphics thing. Not Know Your Variable Types. Where is it? All graphics. There it is. I saw it. Logistic regression is right here where you have a categorical Y and quantitative X. So we're doing the logistic regression part, which is not QQ because that is scatter plots are QQ straight and of no outliers. But logistic actually takes a categorical Y. So what you're seeing right here is a categorical Y. You're seeing probability of being male and you're seeing height. And then what do you notice about the probability of being male? Probability of being male does what with height? So just as you would describe this, and be careful because, well, no one said it yet, but there's not a slope to this line. There is a monotonic relationship such that two individuals, I guess we did a multiple model, who are otherwise identical. We're not doing multiple here. Two individuals who differ in their height by 1 inch, the individual who is taller is more likely to be male. And does that make sense, Caleb? Mm-hmm. And so if I say to you, two individuals who have a different height, the individual who is taller is more likely to be male. And I'm not saying they are male. It's just that if we have two individuals who differ in their height, just let's say 1 inch, the individual who is taller would be more likely to be male. And when we look at this, that means the coefficient for height, because it increases the probability of being male, the coefficient for height is going to be positive. So the coefficient for height right here is positive, where two individuals who are otherwise, well, we don't have multiple variables. So I can just say two individuals who differ in their height by 1 inch. The individual who is taller is more likely to be male. And you can see that right behind my head right there with what we have going on. Is this making sense? This changes because we're not talking about, if you notice what I don't do, is I don't talk about the coefficient anymore, which blows people's minds when you get here. Let's just do this one, which is going to have a weaker relationship. Is not GPA? Oh, GOA. Ha ha. Ooh, that's negative. So what does that mean? So this one's negative. What does this mean? Two individuals who differ in their GPA by 1 point. The person with the higher GPA is what? Two individuals who differ in their GPA by 1 point. And it is very statistically significant. That's what the sigmoidal curve does. The equation for this, I'll show you the equation, and this would be two individuals who differ in their GPA by 1 point. The individual who has a higher GPA is less likely to be male. Once you get up here to the 3 and 4.0 range, you're like, these people are most likely female. Like, and the people down here, sorry. Hey, I'm part of this group down here, but, or they're most likely to not be male. So this curve right here is described by the equation E raised to the regression equation. So E raised to the B0 plus B1 x1 over 1 plus E to the B0 B1 x1. So as just looking at this with any sort of coefficients here, it doesn't matter really, but as the regression equation goes to negative infinity, what will this go to right here? Well, let's do the easy one. Easy one right here. As this goes to infinity, what is E raised to infinity? So as it goes to infinity, and I'll do this in class, like probably later this week class, I'll do this. As E goes to infinity, what's the whole equation? What does this go to? It'll be what over what, basically. And then you got to be like, is it the same this, which it is. Yeah, and this is the logistic regression equation. So it's very much like a lot of calculus and stuff uses stuff like this. Probably you might have seen this in a math class. Just, I mean, these sorts of equations with E, Euler's number, is a very common just because this will bound the curve. And we can see that it's bound, which is some really interesting stuff. So we've got some unique values as the equation becomes, so the equation takes on the values of, as the equation takes on the value of infinity, then the whole thing will go towards what? So if this becomes infinity, then it'll be infinity over infinity plus 1. So it'll be infinity. So what is the limit as the equation goes towards infinity? What is the limit? Well, it wouldn't be infinity. So the limit is going as this equation approaches infinity, because it'll become e raised to infinity over 1 plus e raised to infinity. So you basically have, yeah, exactly, yeah. It's and then as this goes, so you probably know as this goes towards negative infinity, which will make it very, very tiny. Oh yeah. Did you? Yeah, you bet, Kelly, definitely. And as this goes towards negative infinity, what will it then approach as this goes towards negative infinity? As it goes towards negative infinity, e raised to negative infinity will approach what? Because it'll flip it. It'll be, it'll flip it, so it becomes a very, very what number? Oh yeah, no, the e will go towards infinity. Yep, because e raised to bigger numbers will go to infinity. E raised to infinity will be infinity. Yep. And well, and then you might be talking about, because then if this, it'll go towards e raised to negative infinity will go towards 0. Isn't that correct, Kayla? E raised to negative infinity, like if we do, let's do like 2 raised to negative 100. That would be 1 over 2 raised to the 100, because it'll inverse flip it. Does that make sense right there? So that'll go towards 0. Yeah, but since it's probability, it'll be 0. Yeah, is this all making sense? It'll go towards 0 right here? Oh no, it's just, don't worry. Like, mathematics is all the, like, I use this all the time and I teach this all the time, so don't worry. Like, it's so funny. It's like, I had a mathematics teacher who would get mad at us, like, if he forgot like one thing in algebra and we were like, oh, you made this mistake, he'd get mad at us. And it's like, I mean, I make you, what's interesting is I'll make more mistakes sometimes in Stat 201 than I'll make in BAS 320, just because I'll kind of go on autopilot sometimes in 201. So it's like, and I'll be like, oh, I forgot to add this number, I forgot to subtract this number. And if anyone's like, you don't know how to add and subtract, I'd be like, no, I know how to add and subtract. I just, my brain doesn't do it. So yeah, like, no, I don't take offense when anyone's like, yeah, I haven't done this one in a while, I haven't looked over the rules of this in a while, or how this is done. Yeah. And so what is e raised to 0? Like if this right here, like if the equation up here were to solve for 0, just, you know, you can reassign this as like x. Like we just call this, you know, if that's just x and x becomes 0, I'm just saying like that whole equation becomes 0. I know it's so easy. The simple math, the easier it is. The like when it's like partial differentials or something, you're probably like concentrating and being like, okay, gotta do integration by parts, gotta do partial fraction decomposition, gotta go here, gotta complete the unit circle. You know, like you're doing all these things, and then you're like, okay, now I gotta times 2 numbers. What is e raised to the 0? E raised to the 0 is going to be what? Just that alone. Just e raised to the 0, e to 0, because we're saying like this becomes, we're just reassigning this. E to 0 is 1, exactly. So this would be 1 over 1 plus 1. So you know what this becomes right here? It becomes 1/2. And if you notice, these are very important numbers. And these numbers, great job, Kelly and everybody, excellent work. These are very important numbers because look at what we have right here. We have a dashed line at 1/2, and that's actually where we start predicting. We go from male prediction to not male prediction. So the idea of when the regression equation becomes 0, which we can actually find right here, it'd be the ratio of the intercept over the slope. We can just take right here and do this and divide the ratio. And this right here, 2.8, is when it would become 0. I mean, you're just solving, like you would just say, well, if you times this by 2.8, you would add it to the intercept, and then you'd get this value right here. Is it 2.8 or so? Yeah, 2.8. If you times that by 2.8, then you would get this right here. The 50% would be the prediction. And I think what's confusing for people a lot of times is because when you're solving this right here, what you're solving for is the logit P. We'll look at this more, but you have to plug everything into this regression equation to get it. to get the answer, you have to plug e raised to the regression equation over 1 plus e raised to the regression equation. And these questions will destroy people on the test. These are questions that we'll be covering next week with next week's assignment. And when I say predict the probability, like let's say I said predict the probability. We'll just do one more question here, Kayla, because this is where people get really stuck. Let me do the following. Let me make it pretty obvious. Okay, Kayla, predict and use the graphic. We'll do one last question, then we'll do Kelly's, and then we're gonna hop back to 201. Predict the probability of somebody who is 70 inches tall. So I'm gonna put these numbers in the chat for you, but be careful, and then I'll show it again. So predict the probability of somebody being male who's 70 inches tall. Predict the probability of somebody being male who is 70. Predict the probability of somebody being male for an individual who's 70 inches tall. For individuals, so we're saying here that height of the individual is equal to 70. And I might cheat to do it. Sometimes I don't use R to do things. So while you try to do that, I'm going to try to remember the correct code for this, because there's one small change you have to do. And the change I always forget. I don't want to do it too quickly. I don't want you to see the answer. Because there's a common mistake, and I hopefully want to see that you don't make the common mistake. So you have to be very careful, because there's a common mistake. Remember, you're predicting probabilities, so then there's a way to know if you made the common mistake. Like anytime you predict probabilities, think about what they need to be. So try to predict the probability for an individual who's 70 inches tall. Well, I'll make the common mistake first, because then I know how to fix it, and then I'll try to remember the code to fix it. So common mistake about to happen. There's the common mistake. I made the common mistake. And I'm trying to remember the extra argument I need. Let me go try to look at the code real quick to find the extra argument. This is not correct right now. There's something I need to fix about it. And I always forget. Is it that? There it is, yeah. That's it right there. Response gives the predicted probabilities, okay. There we go. It's the right answer. So what happened here, Kayla? When I solved this right here, this is just usual old regression. Let's see, hopefully, Kayla, I haven't lost you. How is this being solved for? How is that being solved for right there? How's that 1.10 being solved for? Okay, no worries. Let me just take the regression equation and write it out. And let me show the steps. This is major important stuff. It will be on next week's assignment. And the answer is up there for how I'm getting the answer. So I'll solve it by hand first. So what we need to do is we need to write the regression equation. So the regression equation is as follows. The regression equation is technically logit. Well, it's technically logit, but I'm going to write it this way. If you write it as a normal equation, you'll get height or predicted height is equal to negative 48.32603 plus 0.7. Oh, and we're doing male. Sorry, that's wrong there. So predicted male, and then times height. I knew something's wrong. Are you with me on this part right here? Are you with me on this right here, Kayla? That all we've done right here. Oh, okay. Are you with me on this right here where I've taken the coefficients and I've written the equation? Are you with me on this portion right here where I've taken the coefficients? Now, there's something I've done that. It's yep. You're seeing it now. So what you can do is you can solve this equation right here. Like you can solve this. If you go through and solve this, you will get, and this is where people usually make a mistake, is if you go through and you plug into here 70, plugging 70 into here will get the answer of 1.1 or something, right? So the plugging 70 into there using the predict function, you get this right here, 1.108. So we get, and then you set it perfectly. Now you have to plug it into the e raised to the over 1 plus e raised to the. So once you get the answer from this, you have to go and take this and go to the e raised to the over the 1 plus e raised to the. And so if we go solve this right here, let's just go and solve e raised to this. Oh my gosh. Okay. So we go and go exp raised to the, and we could just take this number right here over 1 plus e raised to the, and there it is right there. So does that make sense, Kayla? So we literally just took e raised to that answer over 1 plus e raised to that answer. So this is doing the exact same mathematics we have right here, where we do e raised to the over 1 plus e raised to the. The function for that is exp, because that raises e to a value. And you can confirm it's e being raised by doing exp1 and obtaining 2.718, 2.718, 2.718, 2818, 2818, 45, Yep. So this is where people usually make a mistake, where I say something like predict, the height, or predict the probability of someone who is 60 inches tall being male. And they'll usually tell me things like the probability, you can see something interesting here. The probability is negative 5.95. And what's really interesting is when the probability is negative, that means, or not the probability, but when you solve just the equation and it's negative, that means you will be predicting not the level of interest, because the probability is going to be less than 50%. So when the equation, this is just the equation, solves out to a negative number, the probability is going to be below 50%. Does this make sense here, Kayla? Now that you can see that predicting for someone who's 60 inches tall, which is 5 feet, we'd get a probability of less than 50% because the equation came out negative. This is just whatever the equation comes out. If the equation comes out positive, so the probability that a 70-inch tall person is male is yes. On average, for people who are 70 inches, we would see on average 75% of the individuals, like in the law of large numbers, 75% of the time those individuals would be male, or for an individual, we would expect 75% of the time the individuals would be male. And if you take like my height in here and stuff like that, you can see if we predict for someone who's 75 inches tall, then we'd say 99% of the time, like 99% of individuals. And this should definitely look like our visualization over here. So when we make predictions right here, we'd be going up to here and across, and that should be about 99%. Yep. And so you're just predicting the probability someone is male or not male. Yeah. Is it making sense, Kayla? Like, good stuff right here. And I think Kelly had a question. But yeah, that's logistic regression. We'll hop back. We'll do Kelly's question. That is some basics of logistic. That is the basics. For assignment 9, could you please talk a bit more about what should be included in the summary for the variable creation in task 2? Yeah, let me think here. I need to pull up the assignment. I need to take a look. Variable creation in task 2. Let me go get the assignment. And I'll release the next assignment later tonight. Like, part of me just wants to post the older assignments that we haven't redone. But they're a different format. I think that would, I've just been like, we're so close to the end of the semester. Just got to write a few more assignments. We're so close. 2 more assignments. 2 more assignments and we'll be done. Okay, let's see here. Okay. 2 more assignments. Okay. Variable creation. So with the summary, and it was... And then we got some Pearson. Create a new variable and add it to the data frame. Print the head of the column showing the first 6 observations. Add this new variable to your multiple model from the previous problem, provide the summary. Check the p-value from the new variable in the multiple model. Explain the p-value of the new variable in the multiple model, and if you have reason to keep or remove it. And so which part were you specifically wondering about, Kelly? For someone, could you take a bit more to talk about what should be included in the summary for the variable creation in task 2? So you want to add whatever model you have. Like, let's say I have my model previously, because I was working with Just a moment ago, I was working with this model. This is Logistic. Do not make this exact model. I'm too afraid. The summary in part 2. So when you do the summary right here, you want to look at your new variable, whatever it is. Like if you were to add weight to this. So when you look at the summary right here, if you've added a new variable, which you need to make sure this is a created variable, put a note here. Brian is doing Logistic. Don't do... Everyone's going to do it. I'm just too afraid. I've done things like that, and then I've looked the next day and seen like everyone does what I'm doing, and I'm like, no, don't do exactly what I do on the screen. I mean, like, then what are you doing, Brian? I'm just trying to show you here. Let's take a look. Okay, let's bring up a data set. Let's bring up data survey. Yeah, survey 10 doesn't use the numbers. That's why I love it, because you can just type GPA and you don't have to wait like, what number is GPA? No. Exactly right, Kelly. I'm just like, no. Talking concepts here. This is a different data set, so obviously you won't use this data set. Different data set. Okay, that's fair enough. But I'm still doing conceptually the same thing. So previously, you might have had a model predicting height from, let's say, GPA. Height not found because I didn't do data equals. Really? There we go. And so here's the previous model. And we can look at the significance of the previous model right here. Could you go over the... Of course, Jessica, definitely. You got it. We're going to do one... We got another My Pearson problem right after this, but then we'll do that one next, Jessica. You got it. Thank you for asking about it. And so now we could make a variable right here. You know what would be interesting? Close to weight. Okay. We're going to go here and take somebody's desired weight and divide it by... Or let's do their weight first. And divide it by their desired weight. I know this data set well enough that I know the variables. So this is how close someone is to their weight. These people right here say they're exactly their desired weight. These people right here are over their desired weight. These people right here are under their desired weight. Really interesting to look at the distribution of this. So you don't do this. I'm so interested in what I've created right here. There we go. I want to see the close to weight vector. Did someone seriously go down here? Well, we got an outlier probably, it looks like. Okay. So cool stuff with the graphics right here. Let's go ahead and take a look at this new variable I've created. We've got the close to weight variable, how close someone is to their weight. We're going to put that onto the data frame now by going to the following. Go to survey 10. Let's go to close to weight. And then we're going to store close to weight right here. And that's going to store close to weight not found. There we go. Didn't use the capitalization that I used here. So now we've got it stored into here. It doesn't matter that it has a capital. It's just it got mad because the capitalization wasn't there. So now we're going to take this variable right here. And it's probably going to help out, I imagine. And we're going to add in the new variable here. Now let's look at the summary. And what we want to think about is, does this variable bring with it new information? So what do you think here? Can you go to the... Yeah, of course, Megan. You got it. We got the true falses, then Jessica's, then Megan's. You got it. What, does this variable bring with it new information, Kelly? Does close to weight bring with it new information not accounted for by the other variables in the model? And how do you know? Does this new... And it doesn't matter if it does or doesn't. I mean, it'd be nice if it does. But does close to weight bring new information unaccounted for by the other? Yep. That's exactly right. And that's what that p-value means right there. The p-value right there, and this is a created variable. No, you are correct. Yes, it does bring new information because the p-value is lower than 0.05 exactly. We want things to be statistically significant, which means the information it brings is not, like, at least not redundant enough with the other variables, such that it brings with it new information unaccounted for by the other variables. You're exactly right, and that's a small p-value. And this is just scientific notation for 0.002. Excellent job, Kelly. Is this making more sense what I want right here? And we did an actual variable creation right here. So we actually went and created a, hey, what's up, Adam? Good to see you here. We did an actual variable creation, appended it to the data frame. So this was our first model, checking our first model, creating a vector, appending that vector to the data frame, adding that new variable to the model. Okay, perfect. Should I say that it does bring new information? The variable is, yeah. Going through that right there, that the new variable added to the model, if you get a p-value like mine, anything that is statistically significant means that the new variable brings with it new information unaccounted for by the other variables in the model. Exactly. And so that's what we see right here. This variable brings with it new information. Could I go over section? Yeah, I think Presley, we might have time. You got it. We're going to do, I think there was a true-false question. We got 3 things lined up right here. Yours is 4th. We'll try to get to it. So thank you so much, everybody. Could you please go over the multiple choice of what is true about t distributions on the quiz? Let's do it. And the multiple choice about what is true about t distributions on the quiz. And then we got 2 My Pearsons. Then we got a project 1. Multiple choice about what is true about t distributions. And thank you, everybody, for coming by. It's interesting. Sometimes I'll come in, there'll be like 4 people, be like, what? No, it's really good though. Like sometimes like, so what I'm trying to say is like always get here early, and that's the best way to get in the questions. But we're gonna try to. I think we have enough time to get to everything. I think we have enough time. We got our fingers crossed here. Let's do it. Let's work hard. Let's. I think this is it. Okay, I think I found it. Okay. And so I think we have enough time to get to everything. Let's do it. If it's greater than 0.5, it doesn't. Awesome. It doesn't bring with it new information. Great job, Kelly and Adam right there. Let's do this. I believe this is the right question that we were looking for. Which of the following statements is true about the t-distribution? As the degrees of freedom increase, the t-distribution approaches the normal. That is so true. We love saying that the t-distribution becomes the normal or starts to approach it with more degrees of freedom. You can see it approaching the normal right here. And if we go to the classic 95% confidence interval, you can see that it starts to get closer and closer to 1.96. And that is awesome right there. So that is 100% true. The t-distributions are symmetric and unimodal. Well, symmetric, yes. Unimodal, yes. All of them, they're all symmetric and unimodal. The t-distribution have fatter tails and a narrower center. Yeah, Mr. T comes in, says I pay the fool, and smashes it down. There's the fatter tails and the narrower center. It's a little hard to see that it's narrower. That might be the one you're double guessing on, but you can see it starts to get less narrow in the center as it gets more degrees of freedom. And we'll just do this where we go and let's give it very little degrees of freedom. And you can see it gets less narrow in the center. It starts to get kind of a more bulbous center. And so that is true right here. And I think we've done it. There we go. Could you do chapter 14 quiz? The chips one. We got the chips one. We got chips, yogurt, medical research. Let's see here. Chips, yogurt, medical research in that order. Chips, yogurt, medical research. Okay, let's do the 1,000 chip trial. So there's the yogurt. 1,000 chip trial. Here we go. This one is pretty nice because it can be done in jump. So the ones that can be done in jump, we need to go here, copy to clipboard, and then we're going to hit Control or Command C on a Mac. With oh wait. Put the cuts in, makes my life easier. I've literally spent half as much time at night putting tags in videos because yeah, it makes my life a lot easier. There's a knot in my hair. Let's do this. Okay, here we go with the 1,000 chip trial. Let's go ahead and go here to this button where we can copy the data to the clipboard. We're going to do this problem in jump. We're going to hit Control or Command C. Control C on a PC, Command C on a Mac. And then we're going to go here into jump. And when we're inside of jump, we're going to go, it might be hard to see where we're at right there. Let's go here to a data table as though we're in jump and go to File, New, Data Table. File, New, Data Table. From here, we will go to Edit, and this one we will paste with column names. Woo! Don't paste with column names. Don't paste with column names. Don't paste. I was trying to remember. File, New, Data Table, Edit, Paste. Do not paste with column names. Do not paste with column names. Paste. If you paste with column names, it will look like this. It'll put the first value in the column name. Don't do that. And so we see right here, it is blue, and that means it's quantitative, which is good. We want to analyze quantitative data. And let's go here to analyze distribution, double click the variable. Let me slow that down a little bit. Analyze distribution, analyze distribution. And then we'll go here, we'll double click the variable, puts it right there in the Y columns. And next we'll just go to OK. And then we'll go up here to the top right arrow, we'll go to stack. And we could do like our project for a second. We don't have to do this, but we do this on the project. So let's go here to histogram options and to count axis, which will show us how many observations there are. There's only like one observation there. And yep, it'll show you if you do that. And let's go ahead and take a look at the problem now. Okay, so starting out right here, it's asking about the conditions. The data are randomly sampled, so one can assume they are independent. That's why random and independent are basically the same thing. And then we get some distributions which don't look like ours. But if you notice, two of them go from 900 to 1600, and this one is unimodal symmetric, like the normal curve, and it goes up by units of 100. So if you go back to your graphic and you double click this line right here, you can actually change it to 900, whatever the units are, to 1600 by 100. And let's go ahead and take a look at what happens when we do that. And it looks just like that. So they've just changed the bin widths. So this is kind of like with your project. Bin widths can drastically change how things look. Funny enough, this is pretty normal. So, yep, pretty normal looking right there. And evaluate the histogram. The histogram is unimodal symmetric, so one can assume that data comes from that follows the t distribution. We are doing the t distribution, so roughly unimodal. Yeah, and the bottom one says bimodal, so we're not going to do that right there. It says asymmetric. The histogram is roughly unimodal and symmetric. There we go. So yeah, so that's the only one right here. The histogram is roughly unimodal and symmetric with no outliers, so one then can assume it comes from the normal. And the t is a derivative of the normal, so we should be good. Create a 95% confidence interval. To create a 95% confidence interval with jump right here, it actually gives it to us. The 95% confidence interval is right here. If you want to create other confidence intervals, you can go right here and change the confidence level. So right there, you can change the confidence level, and you can choose other and choose other things if it gives you things outside of this interval. So that's kind of good right there for the project. And this is 1156.3. We got that one wrong yesterday. All the way to 1326.3. Let me double check those numbers because that's the easiest error to make. 1156.3, 1326.3. There we go. What does this say? Oh, be careful about this. So what does this say about their claims? So because the interval is entirely above, the mean number of chips per bag is likely more than this. However, the normal model predicts that a small amount of individual bags will have fewer than 1,000 chips. That is true. Because if you look at the data, especially, we've got some bags of chips that are close to there, and just random variation would probably allow for bags of chips to be beneath 1,000. We could draw the normal curve out right here. Let's go here to the David M. Lane real quick. So just understanding what they mean with this last answer is very important. If you're talking about individual bags of chips, we've got here 1240 and 120. Well, you can see here. So using a rounded version of these numbers, Mubot, tell us about the David M. Lane applet. There we go. So if you were to go here and enter in the mean of 1240 and the standard deviation of 120, this is for individual bags of chips, and you would see some individual bags of chips having below this right here. Well, what's very important to know is that we're talking about the distribution of the mean, and the distribution of the mean is different with the standard error, 3.37.55. And we should use a t, but for the moment, this is close enough, and you can see the distribution of the mean is tighter. So the distribution of the mean has a much smaller variation to it. On the project, it doesn't matter if we use the last two of our UT. Either's fine. Thank you, Katie, for asking. Great question. Either is fine. We should get 100 on this. Woohoo! We got it. Was it the yogurt one is next? Katie, great question. Yep, either's fine. As long as it's yours, which I assume it is. The chip one, can you go over the yogurt question? Yeah, yogurt question, let's do it. Was it right here? Oh, wait, no, we gotta cut in the video. Okay, get some coffee. Here we go, coffee time. We're almost out of coffee. You're welcome, Katie. So here we go. Let's do the yogurt question. Here we go. So with the yogurt question right here, we're also doing some jump work on this one. So once again, we're going to go to the button right here. We're going to copy to clipboard. And you notice there is no column name right here. There's no column name at the very top. So let's go Command or Control C. Control C on a PC, Command C on a Mac. I'm just clicking it right there. Then we're going to go down here to jump. And inside jump, we're going to go to File, New Data Table. You can also hit Control or Command N, and we're in the new data table. Once you're in the new data table, don't click inside of it, but go to Edit, and remember we're just pasting because there is no column name. Edit, and then paste. So from here, we have the data inside of jump. Make sure it looks like this and not like this. That's when you paste with the column name when you shouldn't. But if your data looks like this, where it just says column 1, perfectly fine. There's no column name. And now that we have this, let's go ahead and analyze it with Analyze Distribution. There we go. Analyze Distribution, and this will do the univariate quantitative analysis for us, making a histogram. We're just going to double click right here, and then we're going to click OK. So this will do a histogram and give us summary statistics on it along with confidence intervals. We're going to go over here to the top right arrow. Let's zoom in on it so everyone can see what we're doing. Zoom in on. And here we are to the top right arrow. We're just going to go here and go to stack. That puts it in horizontal layout. And I clicked the edge of it, which changed it. That's one of my least favorite things about jump. And then we're going to go right here, and then we're going to go to histogram options, count axis, like we're doing on the project, just to make it look nice. So we can see that there's one observation here, two observations here, 1, 2, 1, 2, 1, 1. There we go. And so now we're good to go pretty much, I think. I'm just going to keep clicking things, aren't I? Let's go ahead and take a look at the problem. Okay, with this problem, it is asking us first about the shape of the distribution. Now, yours might not look like these, but we just need to change the bin widths and everything. These all go from 80 to 200. I think that one included 80 to 200 by units of 20. Let's take our distribution, make it smaller. So 80 to 200 by units of 20. So we go here to 80 to 200 by units of 20. And there we go. Looks like that. No. Wait. No. It's always got to be the one on the edge, doesn't it? Yep, that is it right there. That is the distribution. Good stuff. Got it right there. Next, it wants the normal quantile plot, and I think this is where people usually get confused. A normal quantile plot always goes up and to the right. With that knowledge alone, we can eliminate this one because that does not go up and to the right. We can eliminate this one. That one does not go up and to the right. And then it has to be either this one or this one. This one has a big outlier, so it's probably this one. Let's see if we can get a graphic here by going to the red arrow and going to normal quantile plot. And this is one way to look at the normality of it. They do it a little differently in jump. And if we do this right here, you can see it's starting to look like it. If you start to stretch it, and it looks more like this one over here. I think I can get it on the screen if I do this. And there it is right there. So that's looking like it. They just do it a little bit differently. You can see it's not perfect. You can see the little bend right here. They just have theirs a little bit flipped, but there's not a big gap. Like this one has a humongous vertical space gap. That little gap you see right here is this little gap right here. Like that little space right in here is that little space right in here. You can see just the distances between them also. It's definitely not this one. It's 100% this one. If you're wondering too, these are the actual values over here, and you can see the highest value is somewhere at the 160s, right? 169 right here, and then you've got a 157 right there. This one says the highest value is 169, then there's a huge gap in the data, but there's not because you've got all these values. So it has to be the one on the far right. Are the assumptions and conditions met? The data is random. The probability is relatively straight. So straight and random. This one says not straight, not random. Okay, good. So it's between these two, but the histogram is bimodal and asymmetric. Nope. The histogram is unimodal and roughly symmetric, so the nearly normal conditions met. Find a 95% confidence interval. Good thing Jump already does that for us. We've made our output look all crazy like. So let's go and just go over to where the output wants to be. There we go, 95% confidence. So it's 115.72. 115.72 and 147.37. A diet guide claims that you will get an average of 130 calories from a serving of yogurt? Well, that's in our interval. So I definitely believe that. Yeah. What does this confidence interval indicate about this claim? The confidence interval contains the diet's claim, so the claim is supported by the confidence interval. Yep. Woo! Excellent work. Excellent work. Good to see you here, Jada. And I think we have one more, and then I think we had a question on the project. We'll go to space. So we did the yogurt one, and then the medical research, right? Can you go over the medical research problem? Medical research. Nutrition laboratory. Medical research, you bet. Let's do this. Here we are with the medical research problem. And great job. Jada's already in Hero of Eternity. Love it. Awesome. So with the medical research problem, remember how we interpret confidence intervals? I am blank % confident that the true blank is contained in the interval blank to blank. I am blank % confident that the true blank is contained in the interval blank to blank. So we need to say we are, sure. I am 95% confident that the true beats per minute, true mean heart rate per minute is contained in the interval blank to blank. Yep. That's got it right there. What is the margin of error for this interval? So the margin of error is always what the length of the interval. So I need some help with this. Someone help out. If we have an interval, and usually only make this mistake one time. So if we have an interval that goes from 80 to 100, what is the margin of error? So remember, the margin of error is half the length of the interval. What is the margin of error of this interval? If we have an interval that goes from 80 to 100, what is the margin of error? What is the margin of error of this interval? So an interval that goes from 80 to 100, what is the margin of error? And then always just think about how you solve this. Like, you can probably see it. What is the margin of error for this interval right here? So then always use these like simple problems to be like, okay, wait a minute. The margin, nice job, Megan. Excellent work. You are correct. It's 10. And so with it being 10 right here, just think about what you're doing. You're actually doing the mathematics of 100 minus 80 to get the distance those are apart, and you're dividing it by 2. And that will get you half the length of the interval. Does that make sense? You're just getting, what is the length of the interval? The length of the interval is 20. What's half the length of the interval? Half the length of the interval is 10. So we're doing the exact same work right here. It's just that there's decimals making it look more confusing. So don't let the decimals confuse you. We're just going to go right here to these numbers and say, okay, big number with a crazy amount of decimals. Big number minus small number gives us the distance these numbers are apart. That's just the distance they are apart. So then we just take this distance and we take half the distance. So 1.6, does it only want to one decimal? Look at all those decimals, and it just says, don't worry about those decimals. If the researcher had calculated 90% confidence interval, would the margin of error be larger or smaller? So when you change confidence intervals, if you go from like a 90% or 95, I think it was, and we want to go to between. So if we're at a 95 and we go down to a 90, the interval gets smaller, 68, 95, 99.7. So when you go from 95 to 90, the interval would get smaller. So going from 95 to 90, smaller interval, and that's what we have going on right here. So if they had calculated 90% from their 95, the margin of error would be smaller because you're going 95, 90, smaller interval, and we've done it. We were on fire today. Yesterday, it was Monday. My brain was not awake on Monday. Not supposed to be awake on Mondays. Could you explain section 4, part B and C on project 2? I don't even know where to start, Presley. Let's get this. Let's do it. Wrong button. Okay. Question 4. Let me find. Where's the project? I have to go download the project. All B. Let's go download that project real quick. We have just enough time to do the project. Okay. There we go. And section 4, part B and C. Here we go. Okay. And let's take a look. This is section 4, part B and C of the project. And let's see right here. Create a histogram of the variable total demand and include a screenshot. Your histogram must be in horizontal layout and have account access. Interpret your graphic. Make sure to describe the shape and the appropriate center and spread of the distribution. Comment on any unusual features or outliers you see. If you don't see any unusual features or outliers, mention that. You don't need to remove any data points, only comment on them. Okay, good deal. And we don't have the points associated with each section. Must have are. Okay. So let's take a look right here. And you don't need to remove any data points to go. So what we're doing right now is we're creating a histogram of this. So let's go ahead and just take a data set. And let's go ahead here and go to Analyze Distribution. You'll create a histogram like of age. Ooh, look at that. So this is extremely right skewed. We're just doing kind of the first part, part A right here. And we need to add in a count access to this. I'm doing a completely different variable than you. And we want to go to count access. There we go. So this is an extremely skewed histogram. So the appropriate measure of center and spread would be median and IQR. And I want you to notice something. When you do the appropriate measures of center and spread, there's only two measures that go together. You have here median and IQR, and this is for skewed data, which this is. That is skewed data. That is skewed data. Or you have here the mean and standard deviation, and this is for normal data. So the appropriate measures for center and spread, if it's normal or normal-ish or not too heavily skewed, will be the mean and standard deviation, where if it's skewed data, you will use the median and the IQR. The IQR is going to be 1 right here. The IQR is the distance from the 25th to the 75th percentile, which can be calculated by looking at the distance. These numbers are apart right here. That is the IQR, just 20 minus 19. And if you have trouble finding it or you want to confirm your answer, you can always confirm your answer to the IQR by going here, going to custom summary statistics, and going to the interquartile range, and it will confirm for you the answer is 1 because that's the distance from the 75th to the 19th. So you can also find it over here to like double check. You could probably even add over here if you really wanted the median, but we can see that the median is 19, so it's right there. So you could put these right here and just want to make sure I got the right numbers. Never hurts. You don't have to do that. It's just possible. As stated in section 1, you can assume the randomization 10% condition are met. Clearly state the third condition you need to check to construct a confidence interval of the population for the of the population mean to find the true mean. Explain how this condition is or is not met and provide numeric justification. Regardless of your conclusion, continue to analyze the subsequent parts. So really big question right here is how do we analyze the third condition? Well, third condition the nearly normal condition can be met. It's going to be the nearly normal condition because we're dealing with quantitative data. When we're dealing with quantitative data right here, we need to see, do we meet the nearly normal large enough n condition? So nearly normal is the condition, and the way we meet it is with large enough n. And so right now I have a sample size of 1,905. Although this distribution is heavily skewed right here, I'm bringing up the central limit theorem applet. What this condition states is that when we take larger and larger sample sizes from heavily skewed distributions, we could even make it more skewed. We're not interested, and this looks like mine now. Mine looks something like this. We're not interested in the distribution of single observations. We're actually doing the distribution of the mean of 1,000 something crazy amount. And so we'd actually be looking at the mean for all these observations and the distribution it makes over repeated trials. So we're interested in the distribution of the mean being nearly normal, and the central limit theorem states that the distribution of the mean will be tighter and more normal as n increases, the two things that the central limit theorem states. So the condition is nearly normal, but we meet it a lot of times via large enough n. So it is true right here that we are going to meet the condition because our sample size is large enough such that the distribution of the mean, and I would quote the numbers, If you notice, if I'm going to talk about this right here, I'm probably going to talk about how my sample size is 1,905, and even though my distribution is heavily skewed, the distribution of the mean will be nearly normal because my sample size is large enough such that the distribution of the mean will be nearly normal. Quoting the number there in the shape of the distribution is the most important part with the third condition when dealing with quantitative data, such that we can say that it is going to be nearly normal for these techniques we're about to use. Next, we have to make a confidence interval right here, and we'll talk about interpreting it. So we go to make a confidence interval right here by going to the, let me zoom in on this. Zoom in, we got that? Yeah. Confidence interval on the red arrow, it's second red arrow, and we go to other, and other lets us select different confidence intervals than the classic 90, 95, and 99, and we can enter in here whatever we want. So I'm just gonna enter in 91, make sure to enter in your number, hint, 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 and let's go ahead and go right here and enter it and zoom out of this. Here is the output we need. We definitely need to take a screenshot of this right here, and we get a 90, at least I made a 91% confidence interval for the true mean, and this is the lower, and this is the upper. And this gets us to where we interpret the interval, and we have a great interpretation today. I am blank percent confident. I was so close to it. I am blank percent confident that the true blank is contained in the interval blank to blank. I'll call mine like 18 to or 19 to 20. I am 91% confident that the true mean age of Stat 1 students is contained in the interval 19 to 20, whatever the numbers were, 19.5 to 19.8. But I am 91% confident that the true mean age of Stat 1 students, and make sure to put the correct true whatever it is that you're talking about. This is where I see mistakes. Pretty easy to get I am blank percent confident, and then your interval numbers. But then usually I see the mistakes here that people neglect to realize if they're talking about the mean or if they're talking about the proportion. So we're talking about the true proportion of Stat 1 age? No. We're talking about the true mean age of Stat 1 students because we're dealing with a quantitative number. And hopefully that helps out the questions right here. I think that's got it. I'll be teaching here in a moment. Office hours. Great job, everybody. Lots of questions. Put on, is the music gonna play? That's too sad of music. We'll end right here. We'll end with this music. That's what we'll end with. Yeah. I got this. What do you think about that, Puppet Shark? Puppet Shark, do you have some good office hours? You did? I gotta make you louder, Puppet Shark. You're connected to that music. We got it. Everybody, good luck. Remember, office hours later today. If you have questions, let me know. I will see everybody later. Bye for now. Bye.